Okay, we are Team 2. We did the self-driving remote-controlled car. I am Ryan Abeljude.
I'm Kobe Barrett.
I'm David Quintanilla.
I'm Tuan Trinh.
Okay, so first we're going to go ahead and talk about the hardware. So we decided to demonstrate our software on two different models just to show the flexibility of our software. The first model used structural parts made from 3D printed PLA plastic, and we used little brass spacer screws in between. The drive on it is run by a 3-volt DC twin motor with a gear assembly to help with some of the torque there. So this one is a very DIY low power option. The next Model 2 is made from, the structural parts are made from prefabricated aluminum and fabricated acrylic that we made. It's driven by two 9-volt DC direct drive motors. So this one is a lot more durable, a lot more robust, and a lot more power behind the motors on this one. So we wanted to demonstrate that on two similarly, but still different models to show the flexibility of our software.
About the power delivery, we choose to use 18650 Samsung battery to deliver power for our project. It comes from a reliable brand with a very high quality build and a very economical price. It provides the high performance and high capacity in terms of energy. So the power supply will come from 3 different configurations. So the first one is 2 cells in parallel will provide 3 volts to power the 3-volt DC motor of Model 1. The second one is 2 cells in series. It will provide 7.2 volts, then stepping down with a voltage converter to 5.25 volts to power our main core, the Raspberry Pi 4. The last one is 3 cells in series. It will provide 10.8 volts, then stepping down with a voltage converter to 9 volts to power the 9-volt DC motors of Model 2. So moving on to the next slide is the ultrasonic distance sensor. So for the distance sensor, we select to use the ultrasonic SR04 sensor to create a useful feature for this project, which is distance detection. The sensor will send out a series of ultrasonic pulse and receive the echo from an object. Then the sensor will send the total data to Raspberry Pi 4 to perform its duties. The car will automatically stop, and if the car is too close to an object in front of it, if the distance between the car and the object is less than 10 centimeters, the car will stop moving instantly for the safe purpose. So the next slide is single board computer. About a single board computer, we choose to use the Raspberry Pi 4 as the microcontroller in this project because it's powerful processor in a compact unit. Its size is about a credit card. It contains multiple ports to easily connecting any peripheral device such as monitors or camera. There are 40 pins to be able to connect and modify to be compatible to our project, such as connecting to motor driver and distance sensor. The dual band Wi-Fi connection is useful for the wireless controlling, and the Bluetooth 5.0 connection is helpful for the communication between the Raspberry Pi 4 and the wireless remote control.
Next, we move on to the motor controller. We went with model TB6612 FNG, and it can control up to 2 DC motors at a constant current of 1.2 amps. There are 2 input signals, There's a N1 and N2. Both can be used to control the motor in one of 4 function modes. You have a clockwise, counterclockwise, short break, and stop. The logic supply voltage, or VCC, can be in the range of 2.7 to 5.5 volts, while the motor supply, VM, is limited to the maximum range, maximum voltage of 15 volts. Moving on, we have our USB camera, or 0.3 USB camera module. We use this camera to help and assist with our object detection and lane detection. It's a 0.3 megapixel camera. Comes with a 1/4 inch CMOS OV7725 image sensor for sharp image and accurate color reproduction. Its super small outline and profile are what we use it for and our embedded applications. And it can be used on any platform such as Linux, Windows, Mac, and so on.
Okay, now moving on to the software.
For controller input, we have gamepads, PS4 controllers, as you see on the right. We have 2 of our teammates are using this to control their current vehicles. If you don't want to use a controller, we do have keyboard options that are mapped out to predisposed keys. We can also add more controllers. We just have to map out the event codes that each button gives out. And our inputs can control the speed, direction, rotation, and drive mode of the vehicle. On this PS4, you see there's arrows on the left, and we set those for up or forward, down, or backwards, left and right. On the top 2, we got rotate left and rotate right. Then on the right buttons, we have inputs such as default speed, stop, reset. Then for select button, we have that to switch from manual to autonomous mode and autonomous to manual mode. Also, we had to multi-thread the controller input section of the software because it was getting slowed down and dropping inputs that we were inputting into the system. So now it's has better performance now that it's multi-threaded. And for the motor handling, we use the Raspberry Pi's built-in Python library, rpi.gpio. Basically, what this is doing, it's using pulse width modulation to control how long the on cycle is for the period of time. So for on the right, you see we have duty cycles 50%. It's on for 50% and off for the other 50% of the time, and 75% and 25%. So basically, this is like directly controlling the speed of how fast we're moving the motors. And yes, that's all for that.
Next, we move on to image processing. And just like we described our camera, we're going to describe OpenCV to start. Stands for Open Source Computer Vision Library. And it was originally built to provide a common infrastructure for computer vision applications and to accelerate the use of machine perception in commercial products. We use it to enhance our software for applications such as lane detection and opposite detection. It was used in pretty much all our thresholding and different types of techniques we use throughout our system. And on screen, you can see different pictures in action.
Okay, then moving on to our lane data set. So we did a semi-manual training style, which means that we used a supervised form of learning in our neural net, which that means we have to deliberately classify our training data before our neural net can actually learn from it. Our approach was building some training software that allows the user to manually drive a car around a track. The track is made of 2 lane lines, where both lines are a distinct blue color. As the user drives, the software will rapidly take snapshots from the camera and saves each image to a folder that matches the current drive state. The folder the image is saved to will act as a classifier for that image. Each image is filtered down to a full RGB color image, or from a full RGB color image to a binary black and white image. Using HSV color masking, we can filter out all the colors we don't want, which results in black pixels, and keep all the colors we do want, which results in white pixels. The image to the right is a result of the type of color masking that we use. So now going on to the test and train data sets. We use two very distinct data sets. One is for one for training and one for testing. The training data set will perform matrix gradient calculations, which results in training the weights and biases of our neural net. The testing data set is used to test the newly trained data set on a new set of data that is not seen before. If the results are consistent when training, then training was likely successful. So now we have to move on to the size and diversity of our data sets. Diversity is a very important thing for all data sets. Training too much on specific conditions will result in inconsistent results. Therefore, the data set must include images from a diverse set of scenery and lighting conditions. The size of the data set is also a factor in the success of the neural net. Each scene needs around 3,500 to about 5,000 images to achieve reliable results. More than 5,000 images results in data biases. Less than 3,000 images results in too much uncertainty. So now we can actually talk about the convolutional neural net. The machine learning framework that we ended up working with was PyTorch. PyTorch proved to be a very effective and very well documented framework, which was great for our development. Now we can talk about what a CNN is, and I will actually go in and explain some other common neural nets before I actually explain the CNN, just for reference. So the artificial neural nets, for an artificial neural nets, that accepts one input, one output, which is very good for simple one-dimensional data, but not as effective for more complex data, such as our situation with multi-dimensional images. The next one is recurrent neural networks. These make inferences based on the current data and the previous inference that it made. This is most effective for text-to-speech or autocorrect applications, but not as effective for our application. Now, a convolutional neural net can accept multiple layers of data as input and output a single data point. This was perfect for our application since image data is multidimensional and each inference should result in a single drive state direction. And now we'll actually talk about the effectiveness of the CNN. Our original solution actually didn't include a CNN at all. We actually used a dot matrix of all the we created a dot matrix of all the pixels in an image where a lane is detected. Using the least squares fit formula, we could summarize the dot matrix into two lines that we could then perform geometric calculations on. The calculated lines could then be plugged into a quadratic formula and the radii of curvature equation to get an angle curvature in degrees for each lane and a lane center offset for the whole vehicle. This worked very well for the most part, but limitations in our camera's viewing angle resulted in lanes being out of view when we were actually trying to make the turn. With no lane in view, our curvature calculations fail as a result of not having enough data to actually calculate on. The final result of this method was actually very effective and consistent drive while on a straight path, but highly inconsistent drive on curved lanes. So this limitation led us to begin research into convolutional neural nets, as they can infer a correct drive state using significantly less data than our curvature calculations. The result, while a little less informative, proved to be far more successful and consistent in autonomously driving than our original curvature calculations. And here we just have a couple short demos we can show of the cars actually driving in an autonomous state around our track. So this is our Model 2 driving around the track. And then we have Model 1. Okay, so in conclusion, we built a flexible software model that can be applied to any vehicle of any size as long as it includes a differential drive and a camera. This software model succeeds in autonomously driving within a lane while leveraging our trained neural network. We hope the software solution eliminates any forms of distracted, disabled, and impaired driving to increase the safety for all drivers on the road. And that's it. Thank you very much.
Thank you.
Thank you.
Thank you.